I want to talk to you about a theorem from George Andrews' number theory. As I was flipping through the pages, nothing stood out more to me than the figures on Wilson's theorem. I discovered that Wilson's theorem states, if p is a prime, then p divides p minus 1 factorial plus 1. So my questions were, what do these figures represent? How are they created? And how do they prove Wilson's theorem? Before I go into this, I would like to tell you a little bit about who came up with this theorem. Wilson's theorem was published in 1770, surprisingly not by someone named Wilson, but by Edward Waring, in Meditationes Algebrae. Waring did, however, regard belonging of this theorem to John Wilson, one of his students. Waring didn't prove this theorem until 12 years later in his third edition of Meditationes Algebrae. However, it is said that Leibniz made a very similar conjecture about prime numbers nearly a century prior to the publication of Waring's work. Now let's take a look at the proof based on those figures I saw in Andrew's text. Let's first assume p is an odd prime, because if p equals 2 and we plug it into the theorem, it states 2 divides 2. So how about we let p equal a larger prime? Let's say 5. To help us prove why 5 divides 5 minus 1 factorial plus 1, let's first recall that a 5-sided polygon with 5 vertices is a pentagon. Now, let's consider how many stellated pentagons we can draw in a circle, with 5 line segments connecting to 5 evenly distributed points in the circle. But what is a stellated pentagon? Stellated means that the line segments of a pentagon are able to cross each other, as long as it has 5 line segments and 5 vertices. This is useful information as we can use the number of stellated pentagons on a circle to help us prove Wilson's theorem. And in our example, prove why 5 divides 5 minus 1 factorial plus 1. With this circle, we can answer the question, how many stellated pentagons can we create with these 5 evenly distributed points by first choosing a starting point and connect each point with a line segment. Since there are 5 initial starting points to choose from, then 4 points to choose to connect to after the initial point is chosen, 3 points following that, and so on, we can say that there are 5 factorial different stellated pentagons on the circle? No, because we haven't considered the fact that from each starting point on each stellated pentagon, there are 2 different paths. Meaning, with each of the 5 initial starting points, there are 2 line options to choose as the initial line segment. Therefore, there are 2 ways of coming up with the same stellated pentagon. So, rather than 5 factorial different stellated pentagons, there are actually 5 factorial divided by 2 times 5 different stellated pentagons. As you can see, there are 12 different stellated pentagons. These are created by connecting the points with line segments and creating as many different arrangements as possible. After that, we can take each starting point and rotate the pentagon by 2 pi over 5 to give us the different positions of each arrangement. But let's take a further look at these bottom 2. If we rotate these by 2 pi over 5, we would come up with the stellated pentagons with the exact same position with each rotation. The shape would stay the exact same. We call these regular stellated pentagons, as they don't change position when rotated 2 pi over 5. When considering regular stellated pentagons, there are only 2 options: connecting each point with the point directly next to it, or connecting the points by skipping 1 point each time, forming a star. The number of regular stellated pentagons can be derived from the formula 5 minus 1 over 2, which tells us there are 2 regular stellated pentagons. This formula can be proven by considering a regular stellated pentagon on a circle, drawn by connecting the line segments with points directly next to each other, skipping no points, and splitting the pentagon in half through the diameter beginning at one of the 5 points. More regular stellated pentagons can be created by skipping more points as the line segments are connected. But if the first point that you connect the original point with passes the diameter, then it will not produce a different pentagon. And in this case, we'll just repeat one that is already created. Therefore, we can say that the number of regular stellated pentagons will be the number of points on either side of the diameter line. In general, the number of regular stellated polygons that can be created on a circle with p equally distributed points in p line segments is p minus 1 over 2. But why does p have to be prime? Well, the problem can be seen when considering the creation of the regular stellated polygons. If you consider p as any composite number, let's say 9, and start creating regular stellated 9-sided polygons by first connecting points with line segments skipping no points, and then by skipping 1 point, and then by skipping 2 points, you will see that the line segments will infinitely connect with only 3 points, forming a triangle, which only has 3 sides and 3 vertices. With any composite number of points, there will be a certain number of points skipping that will construct a polygon, where the number of line segments is not equal to the number of points on the circle. To find the amount of irregular stellated polygons, we can find the difference between the number of stellated polygons and the number of regular stellated polygons and divide that by p. We divide by p because we want to prove that p divides p minus 1 factorial plus 1. And it turns out that this can be divided by p, since the number of polygons is dependent on the number of points. This is because there are p number of points, so each irregular stellated polygon has p different positions if you were to rotate it by 2 pi over p. Once you do some basic algebra, you will see that p does in fact divide p minus 1 factorial plus 1. Thank you very much for listening to my proof of Wilson's theorem.